let us talk about the Euclidean algorithm, which is a way of computationally finding the greatest common divisor of two numbers. Now, this is based on a very simple observation, something that we have looked at already. So, let a and b be integers. We could even look at just natural numbers. So, let us say a b be greater than or equal to 0, at least one of them is non-zero. Okay, and what is the objective here? What we want to do is to try and find the GCD of these numbers, and to do this sort of by an algorithm, a computational method. What we do is something that we have done once before already as part of one of the proofs, which is, so the broad idea is the following: we try and reduce the size of the problem. So, reduction of size. So, we have two numbers a and b, maybe they are largish numbers. Our first goal is to somehow make the numbers smaller, but the GCD itself should remain the same. Okay. So, here is the formal way of saying this: the GCD of two numbers a and b is in fact the same as the GCD of a minus b and b. So, this is something that we did earlier when we were trying to write things of the form ma plus nb and so on. So, if you have the numbers a and b, you keep, let us say, the smaller number as it is. Suppose b is the smaller number, you keep b as it is, and you reduce the size of a by replacing a by a minus b. That is usually how it is used in practice. But the lemma itself is in general, I mean a and b can be anything. I am not assuming b is smaller or a is smaller, etc. Just take any two numbers a b greater than or equal to 0, not both 0, then the GCD of a b is the same as the GCD of a minus b and b. Okay, so let's prove this. So, let us call the left hand side as something and the right hand side as something. And now we have to prove that d is equal to e. So, that is our goal, want to prove d equals e. Okay, so let's start. So, d is the GCD. In particular, it means that d is a common divisor, d divides a and d divides b. Okay, so that just comes from the fact that d is the GCD. What does this mean? So, we have looked at this before. If d divides a and b, then d certainly divides their difference. Okay, and it also of course continues to divide b. So, I am just rewriting the bottom equation as it is, or the bottom relation. Now, what does this tell you? This says that d is a common divisor of, so this says that d is a common divisor of a minus b and b, but e is the greatest common divisor. So, that means that this is less than or equal to e, because e is supposed to be the greatest of all the common divisors. Okay, so, we have proved one direction, we have shown that d is at most e. Now, the converse is sort of similar. So, we just look at e and d likewise. So, look at e was a common divisor, meaning it divides both a and b. This means e divides the sum of the two numbers, again one of the properties we have looked at before. So, the sum is just a in this case. So, e divides a, and the bottom I carry over as it is, e divides b. Together this means that e divides both a and b, it is a common divisor. So, same argument, a b, but then d is supposed to be the greatest of the common divisors, and so I conclude e is at most d. So, together, so I have proved both directions, therefore, I have shown that d is equal to e. Okay. So, what this really does is the following: it says that to compute the GCD of two numbers a and b, I can make my problem a little smaller by replacing the number a by the number a minus b. Okay. So, this is a reduction of size step. but in fact one can reduce the size in one go. So, let us apply this lemma repeatedly. So, what do I mean by that? Let us formulate that as a corollary. In fact, I can do this is the GCD not just of A minus B, but A minus any multiple of B. This is true for all k greater than or equal to 1, for example. So, why is this a corollary of the previous lemma? The proof is you just apply the lemma again and again. So, apply the lemma repeatedly. So, this is the sort of argument which occurs in many places. So, once you know a certain statement, you just see what happens when you keep applying that statement again and again. So, for instance, the statement that we know is this: the GCD of two numbers is the same as the GCD of their difference with the second number. Okay, but now I think of these two as my two new numbers. So, I think of this as my new number, let us call it A prime, this as my number B prime, and I apply the lemma again to these numbers. So, this is equal to the GCD of their difference. So, A minus B comma B. Okay, but what is that? That is just GCD of A minus 2B comma B, right. So, this is A minus 2B and that guy is B. Now, I apply the lemma again, I get GCD A minus 3B comma B and so on. Okay, so, you can sort of see how this argument works. You just keep applying the lemma repeatedly, you get this. But here is a nice little exercise: prove this using induction. Prove this corollary using induction. So, you will just have to set up the arguments in the framework of mathematical induction, assume it is true for k and then show it is true for k plus 1. Okay. So, but the basic idea is really just applying the lemma. Okay. Now, what this says is that I can really compute the GCD of two numbers by performing a large reduction of size by just replacing the number A by the number A minus some multiple of B. Okay. So, let us see how this reduction in size really works in practice. So, here is an example. If you had to find the GCD of say 189 and 35, well, what you could do is to say, okay, let me try and reduce the size as much as possible. Okay, so 35 is a smaller than two numbers, I keep 35 as it is. I know to reduce the size of the first number, I can replace 189 by 189 minus some multiple. So, I do not know which multiple, whatever multiple I want, but let me try. So, I am just calling that multiple as star in this case. So, my question is how should I choose this multiple so that this number becomes as small as possible. So, that is the goal really, right. So, I know I can pick any multiple whatsoever, but which one will ensure that I get the smallest possible answer there. So, that would be the most optimal way of doing it, right. So, let us see what would we do. We have 189 minus which multiple of 35 will give me a very small answer. Well, if I for example took 5 times 35, okay, so the multiple 5 of 35, so that is going to give me 175. So, 189 minus 175 is 14, okay. And if you sort of think about it for a little bit, if instead of 5 I replace 5 by any other number, okay, smaller than 5 or larger than 5, then this number that I am going to get here, I mean this number could become negative, but whatever it is in absolute value, you can never get anything better than 14. Okay, you are always going to generate numbers which are bigger than 14 in absolute value. Okay, somehow this is the best possible number that you can generate in the form 189 minus some multiple of 35. Okay. Now, so how exactly am I doing this? Well, we'll come back to that, but let us keep going. So, what have we done here? We have said GCD of 14 and 35. Okay, so that is the first step really. Now, GCD of 14 and 35, we can use the same idea. I can replace, I mean that is the same as GCD of 35 and 14. and now I do the same thing. I try to replace the smaller, I keep the smaller number as it is and replace the larger number by 35 minus some appropriately chosen multiple of 14, so that this number is as small as possible. So, I want a reduction of size to the best possible extent. So, now what multiple of 14 will give me something small? Well, 14 2s are 28 and 35 minus 28 is a 7. Okay, so I do that. So, I take 35 and write it as its 14 2s are plus an extra 7 there. Okay, so this is just GCD of 35 minus, so I am going to take 2 times. So, 2 is my, so thing I have chosen, the multiple I have chosen is 2 in this case. Okay, so GCD of 7 and 14. Okay, I could keep going. I mean, here it is already small enough that I can find the answer directly, but let me just keep going. This is GCD of 14 and 7, and now I do the same thing. I keep 7 as it is, replace 14 by 14 minus some multiple of 7, which will make this number as small as possible, and that multiple is of course just 2 times 7, so that this is the GCD of 0 and 7. Okay, and remember the GCD of 0 with anything, well, let us just see what that is. By definition, that is just the number 7 itself. Okay, why? Because 0, every number is a divisor of 0, right? That was one of the things that we observed earlier, that every number, every integer is really a divisor of 0. And 7 of course only has, in this case it is a prime, it has got plus minus 1 plus minus 7 as its divisor. So, the only common divisors are the numbers plus minus 1 plus minus 7, the largest among them is 7. Okay, so what we have also used here is this little fact, as follows from the definition, that if I take the GCD of 0 with any non-zero number, the answer is just B. Okay, for any natural number n. If B is a natural number, the GCD is just B. Okay. So, what this process now does is really allow you algorithmically to find out the GCD of 2 largish numbers, in this case 189 and 35, by successively making the size of the numbers smaller. Okay. So, I had 14 and 35, next step was 7 and 14, and then that became 0 and 7. So, the successive size reduction finally allows you to calculate the GCD by reducing one of the numbers to a 0. So, if you keep reducing the size, eventually one of the 2 numbers will become, the smaller number will become a 0. Okay. So, this process which we have done in this example is what is called the Euclidean algorithm. Okay. So, we have seen it in this example. What we will do later on is to actually write out an actual proof that this always works.